So with several different pieces of connecting equipment, we're back. Thank you for enduring. This is work with input from quite a few people. I'll be talking about remote sensing of winds. So winds, you've heard earlier today, are kind of important for ocean modeling. So why use winds from a satellite, right? Because model winds are really easy to work with. They have data everywhere. They're on a regular grid. That seems super. The problem is that they are less than perfect. Of course, satellite winds are too. If you have even a small bias in your winds for some applications, like coral bleaching, it can have an incredible difference in the temperature you estimate in the surface of the water, up to a degree difference. For longer term applications, yes. So we also established my shape of my head is very different than John's. The longer term mean, of course, you can get really large biases. So you want to look and see how well the models do, and we can do that by comparing them to wind data from satellites. So this is work by Dmitry Duchovsky, and I'll give an Arctic example to show something different. In the upper left, you see a picture of quickscat average winds, that's satellite winds. And then there's three different numerical weather prediction products. There's the old INCEP 1 model, which folks that do Arctic research love, because it's a really long time series. There's the more modern CFSR, atmospheric forecast, and then the Arctic surface reanalysis, which is the thing for the Arctic. And in the bottom right corner is CCMP, which is a cross-calibrated multi-platform wind product. So somebody's intercalibrated, Frank Rentz at Remote Sensing System and his team have intercalibrated a whole bunch of satellites, and they're throwing them all together with actually a fairly simple variational approach to get wind fields that cover all space over the ocean. So these are different pictures. Now this is pretty clear that the satellite is not consistent with the numerical weather prediction products in this case. Now some of the differences are because the, oh, you can't see that, sorry, I've got to move ahead. So this is what I was just talking about. So here's the satellite in the upper right. This is the new Arctic reanalysis. This is a satellite-based product, and these two are NWP. This is a really old NWP product. And they look very different. Part of the difference is because they have data over ice and they're just handling ice differently or not handling at all. But where there's no ice, which you can get from the quickscat image because it doesn't take data over ice, then you can start looking at the differences. And these are big differences in terms of this color scale down on the bottom. So that suggests that you might not want to use some of these for ocean forcing. The speeds are far different. So Dmitry also looked at the directions. And the color here indicates a shift right or clockwise or counterclockwise in direction. And you can see that white is good. So that means yellow is a shift one way, blue is a shift a different way. And the original INCEP reanalysis has a quite substantial shift in the wind. If you think that curl is important, this is really, really bad because it won't preserve the curl. It'll do terrible things. CFR doesn't do too well. Arctic reanalysis isn't bad, but even the satellite-based product is not consistent with the satellite data entirely, and that's because of some of the trickery. So let's look at satellite data now. This is an example of two satellites. One was quickscat and one was Audios 2 that were up for about 8 months, 6 to 8 months at the same time in orbits that were really complementary. We have other cases now where two satellites are up, but they're in almost identical orbits. That doesn't help as much. So the blue is, I forget which one. Blue is Midori 2, and red is QuickScat, and they fade to white after 12 hours. Because back in the early 2000s when we did this, 12 hours was, after that, data assimilation didn't want to touch it. It was too old. That's changed a lot, hasn't it? So they use data from 3 days, 5 days now. So this is a really cool animation because you can see the coverage is just exceptional from this. There's a huge amount of data if you can use a constellation that's intercalibrated. So we go to great lengths to intercalibrate these data sets. And I'm not going to address it too much, but the biggest problems only happen after about 20 meters per second in wind, which doesn't happen very often. So if we try to use these now on a shorter time scale and grid them, this tends to be the perspective people get. In this white, you get nice vectors that are good and easy to work with, and then there's these gaps. And you can't force an ocean model with that. It's like having all these sea monsters in the gaps, and it doesn't work. So you have to do very clever things to fill this. Actually, if you work with a really old model that barely gets synoptics right, it does work, but that's not where we're going at this meeting. So things have to be done to fill in those gaps, and Tony's going to write a proposal to do that this month. One of the things that comes out of people using wind products is that when we call them wind, they think they're wind. How many of you are aware that when a satellite person says we're measuring wind, we're not really measuring wind? Any hands want to go up? Okay, there's a few. So it is calibrated to wind. No, it's not. Okay, it's something else. It's not wind, and most people run with it. So I'll give some examples of what problems this does. For atmospheric scientists, it's not a big deal because of the memory issues are minor. But for an oceanography, it's a real problem, particularly if you want to go to long-term changes. So what we use is called equivalent neutral winds, which is not equivalent to neutral, so it was a very strange name. But it's a 10-meter wind is what we calibrate things to because that's traditional. The World Meteorological Organization says we want a wind at 10 meters height. Now, the winds change with height, so you have to pick a height that makes sense. They decrease as you get toward the surface, typically. And they change depending on the stratification. And a satellite doesn't measure that stratification, and it certainly doesn't measure a wind at 10 meters. Then we adjust it to that. And after we define this equivalent neutral wind, it's within usually half a meter per second of that actual wind. But there's systematic changes, which will depend on the changes in sea surface temperature, changes in the air, and you want to avoid that. So to understand it, you have to have a lot more information about boundary layer meteorology, and that's tomorrow's lecture. So probably on a different computer, maybe. And we'll go over how the physics for that works. But it does cause systematic errors. And if you were to try to calculate a heat flux, a turbulent heat flux, it would cause about a 10 watt per meter squared average error in mid-latitudes. That's pretty big. You do not want to do that. So how do you find out about this stuff? You could read the journals, but almost nobody says anything about that in the journal unless it's the topic of the paper. You could go to the user manual, but it just says it's calibrated to equivalent neutral winds. You could go to the metadata, and it'll say maybe equivalent neutral winds. Usually it doesn't, actually. So the metadata is great for everything else, but it really doesn't define what the product is. And having just taken all the satellite altimeter or the scatterometer data and put them into a common readable format now, so anybody can use one read code to read them, trust me, it was never in there. The easiest way to find out about these things in general when you're working with a satellite data product is talk to an expert. So if you wanted to find out about winds, people used to talk to me, but I trained a graduate student to answer all those questions, and he now works at the PODAC. You can ask him. It's taken a lot of time out of my hands. If you want to talk about sea surface temperatures, talk to Tony or some of the other experts at the PODAC. And before you embark in something exciting with the satellite products, I really encourage you to actually find out what they really are, because it's not always what it seems. So I'll talk about different ways of measuring these winds. They're all intercalibrated to equivalent neutral winds, so it's convenient once you get it. But they're measured in very different ways. Radiometry gives you scalar winds, or speed. And what it does is measure how much energy is being emitted from the surface, and that's a function of the temperature of the surface primarily, and then the roughness and the white capping on that surface. So the more white capping there is, the better emitter it is, and that happens at higher wind speeds. So it can be used to measure wind speed. And it's pretty good down to about 3 meters per second. There is a special type of radiometry called polarimetry, where it measures more characteristics of the surface emissions. And you can actually get a direction from that. And it's, the directions, though, are only accurate down to about 8 meters per second. How much of the winds over the oceans are below 8 meters per second? So how about if you're a tropical meteorologist? Maybe all of them almost? So, so this is not a good thing for a tropical guy, but for a high wind, mid-latitude person, this is good. Okay, just work with the data that's useful to you. But the speeds are pretty decent. So in this particular example, it's a movie I cannot, I can run, I've got the mouse, maybe. Apparently not. Okay, so this is a picture of QuickScat made by David Long, and it is a radar. It's an active sensor. It sends out a pulse down to the surface, and it measures the fraction of that energy that comes back. And it does it at 2 different angles, and it rotates as it does that, and it moves. So if it was moving in this direction, which in this picture it should have been, it would sense, say, here, with this outer beam, and then as the satellite moved further along, it would hit it with the inner beam, and as it moves again further and further, the back end of the inner beam hits it, and then the back end of the outer beam. So it gets to look at the surface from different directions. And that's useful because the surface has different characteristics relative to the wind direction. So by looking at it at different directions, we can figure out which way the wind is blowing fairly accurately as things go. And from that, we can get a vector as well as the speed. Now, the advantage of this is that in radiometry and in scatterometry or any other remote sensing technique almost, the speed changes depending on what their wind direction is relative to the satellite. So you really want to know this direction to get your best speed. So this kind of solution is fairly good for that. The downsides of this is that it doesn't work right near a coast for like any of the other remote sensing techniques. It has about a 25-kilometer footprint, so it maybe can get within 15 kilometers of the coast. So for coastal oceanography, we still want to make an instrument with a finer footprint. We're trying to get one up with a 5-kilometer to 3-kilometer footprint up. Be much better for coastal oceanography. Synthetic aperture radar. This can get you, or SAR, can get you really close to the coast. It can measure things down to 10 or hundreds of meters usefully in some cases, sometimes bigger. But the directions aren't really accurate. They can easily be all shifted by 7 degrees or 20 degrees. But for feature detection, it's great. So a lot of the grad students working with this in Germany were saying, you know, hey, look, I can see the wake of this little pirate ship heading toward that commercial transport. They could find the tiniest features in there, oil spills, that kind of thing. It's great for that. So for an operational application where you want to see if somebody's dumped oil at sea or dumped waste from their ship, this is great. I would not use it to force an ocean model, though. One of the newest things that's come up is a new satellite called Cygnus. It was launched last year. It's been up for about a year. People are trying to calibrate it. And it takes signals from the GPS satellites that are bounced off the surface and then retrieved by a different satellite that's flying in formation around the world, and it's focused on tropical applications. So this is an example where you'd have these satellites flying along here. A signal comes from a GPS satellite, bounces off the surface, hits that satellite, and it gives you these tracks of winds like this scattered around. So the more satellites you would have, the greater number of tracks of winds. In this case, there's 8 in the constellation, and it's, for doing some things in the tropics, it's awesome because you get a lot of coverage. Now, one thing to remember when you're doing satellites is that if it's in a low Earth orbit, anything from a spy satellite up to about as high as you can go and be low Earth, it takes about 100 minutes to go around the globe. That means even if you've got your satellite set up to go over the same spot over and over and over again, which is hard to do unless it's going over the tropics, it's going to take 100 minutes to go between those. So with this constellation, as it spreads out, you can get better sampling in time. However, not so much in space. It's very interesting, and you get winds, and a lot of them, but they're not in a pattern that's easily converted to a curl. You can't take a spatial derivative except along the track. So again, for oceanography, that's not good. So for vector winds, we have the only essential variable that has the same name as a cartoon villain. So this is from, I forget the name of the movie now, but entertaining. So what are some of the real applications? On a larger scale, you can look at ENSO forecasts, and people take altimetry to get the geostrophic flow, and scatterometry to get the Ekman flow, because the curl of the winds will give you more of that Ekman flow. You can combine the two, and you'll get an estimate of the currents. It's not quite right. This is an older result from Fabrice Beaujean, and these would be the anomalies. And once you have the anomalies, it's very easy to say what the INSO phase is. Of course, at this meeting, we want to look at smaller scales. So let me give you an idea of how to work with the swaths. Most people don't like to do that because it's not regularly gridded. Even these swaths, even though they have, say, 176 points across, all the way across the swath and down, they're not on a regular grid still. And you can interpolate it to a regular grid if you want, but the further you interpolate that data, the bigger your error is going to be in any derivative calculation. So there's a lot of reason to get these derivatives. The curls drive the Ekman upwelling. You get the impacts on deep ocean transport and the like for stress. So this is easy to convert to stress, by the way. I'll show how to do that tomorrow. Again, since they're so well intercalibrated, it's easy to work with the constellation. So I'm going to go over how to work with this to calculate a divergence or a curl. In this particular example, I'll do curl. And a trick which is taught in oceanography all too often is that the curl is equal to the circulation divided by the area about which it is circulating. And we can simulate that with the vector motion. We can take then this dot product around any area we care to define and get a curl. And it'll be an area average curl, but it's pretty effective. Well, some of the time. The math is simple when you have it broken down into vector components, and you can define any shape you want. I picked roughly circular shapes for this work, or my grad student did, for two reasons. One, the error characteristics are optimized when you have the largest area to perimeter ratio, and that you get with a circle. And two, we were looking at tropical cyclones, which are roughly circular. So this is where we started with. And you can see the darker part here maybe that you can take the shape around. Now, this shape here gives you the identical answer to a finite difference, which is what most of us use, except that I haven't had to interpolate anything. So my finite difference is going to be a little bit better if you don't interpolate. But if you don't interpolate, it's identical, as would this one be. Now, if we're doing finite differencing and you work with satellite data, some of the satellites don't work very well when it's raining. So people like to remove the data where it was raining. So let's say we remove this point. So I'd still have my big circle like this if I was doing a circle that wide. And with this point missing, I would also have an inner circle circulating in the opposite direction if I was doing finite differencing and averaging. Because normally, all these interior points get canceled out when you're taking a curl. And only the outer points matter. So if you artificially remove one of these inner points, you are now adding a whole nother circulation to the calculation that is the opposite of what you should be getting, probably. So it's going to give you a terrible circulation. So a lot of people do this. Don't do it. Don't remove the points. It's not going to matter anyways if it's the outside point, because it's not going to have any impact on your answer. That's not touching any of these points. If this was on the edge of your map, you could remove it and then interpolate between them, and we have the code already set up to do that. That's safe, but you can't remove an interior point. Now, with this particular code, we don't go to the interior anyways, because I only work in circles. But if you were doing finite differencing, which is what most people do, it's an absolute disaster. So if you do that, and you remove places where it rains, where does it rain? Well, tropics. And what type of circulation is associated with rain usually? Fronts. Is there a sign to the rotation? Somebody's saying something. There is. It's a cyclonic rotation. And if you remove all this cyclonic rotation from your ocean forcing, what's going to happen to your ocean? Oh yeah, that's not good. Okay, so we don't want to do that. So don't remove the points. Use a smarter method that's more robust when you're trying to calculate these vorticities. By the way, this technique will work on a map that's gridded as well. You don't have to do it on swath data. It works anywhere. So let's see some examples of this, because it's not perfect. So I worked with an older version of the SeaWinds data set, and I wish I could redo this with a newer version because it's astronomically better. So my other message with this is, don't work with the old data. The newer sets are so much better that you shouldn't do that. So when I'm reviewing papers, I say, which data set did you work with, when the author doesn't tell me? And they say, I worked with the old one. We say reject. It's very straightforward. So this one is, I'm working with as a 25 by 25 kilometer spacing. The newer is 12.5, and it's just a lot better product for many reasons. There's all kinds of missing values. Anyways, the newer stuff works better, even when it's raining, which is really neat. So I have this warning here just to remind people later when they're seeing this that this old version is much worse. So what we have here is a warm core seclusion. That is an incredibly powerful cyclone. Usually at mid-latitudes, rips across the North Atlantic in a day or a day and a half, 2 days maybe. And the big ones are make Texas look small. So they're very, very big. You can see here a trailing front from it. And if you could see through the haze of vectors, you'd see a big circulation. When I show vorticity, it's much more obvious. So this is what happens if you're doing a finite difference. The finite differences are not cool. So this is working with the smallest grid scale. Don't do that, because the noise is horrendous. This is what happens if we start working with a diameter that's 2 grid cells in your data, and this is a diameter of 3. So this is where it starts to look good. The signal to noise comes much better when you go to 3 grid cells. So when you start smoothing vorticities, this is a clue. The ECMWF folks do the same thing. When they plot their data up, it's not on a regular grid, and they find smoothing to 3 grid cells has been the answer. And the reason for this, we can go through in papers and show you what the air characteristics are. I'm not going to do it today. And then this is 4. It gets smoother and smoother. So depending on whether you really like synoptics or more mesoscale, you can smooth it out. But in this one, you can see this front coming around. It's trailing back here. This is a different swath where you see it overlapping a bit here and trailing over there. And it's you can get some pretty good feel for what should be in your product. So we can use these to see what's missing at the same scale, because we can filter everything to the same scale in the other products. I'm going to skip this slide on error characteristics, but I'll give the punchline is that the observational error is not dominating. It's our approximation of a linear fit between the 2 points that's dominating the error. If we go to 1/5 the resolution, then they'll be matched in scale with the 25 kilometers. So our 5 kilometer goal would be kind of optimized for that kind of solution. We had a couple efforts to get satellites up that had 5 kilometer and then 1 to 5. None of these got funded because they cost too much. We're now trying to get one up that has a 5 kilometer resolution and measures currents at the same time. That'd be 5 kilometers across that whole swath. If somebody wants to use the code, the place where it is in these notes, and you can get it. There's a MATLAB IDL and one other version I couldn't remember at the spur of the moment when I was trying to do this. But if you convert it to something else and want to share it, we're happy to give you credit and put it up on the website. But this is a really nice tool, and the IEEE, the engineers, are starting to make these things available as well. So what's another application of winds? You've seen Dudley Chelton and Larry O'Neill and many others maybe talking about sea surface temperature fronts. So this is cold water here, warmer water up here. Winds blow across fronts all the time. And in some places, the divergence changes because of it. If it's coming perpendicular, and if it's moving parallel the front, the curl changes. And that has a big impact then on the ocean response, of course, as well. If you go to a meeting where people focus on this topic will get senior scientists fighting with each other more often than any other one, because people don't know why this happens. You actually, see relatively calm people get up and yell at each other. So why does this happen? I'm not going to read all these. I will sum it up, though. So this is Larry O'Neill's list. He's done a nice job putting it on this. He has the seminal paper now looking at the physics behind this, or eliminating some of the physics. He doesn't actually come up with the answer of what works. But almost all these ideas break down into 2 cases. One is the atmosphere slave to the ocean, or 2, does the atmosphere move on merrily without changing as it flows over a front in terms of thermodynamics? So is the sea surface temperature, is the air temperature adjusting to the sea surface temperature, or is it not? And one gives you a pressure gradient effect, and the other gives you a stability-related effect, so more turbulence or less turbulence that transports momentum up and down and causes those changes. So people have looked at this. We've actually managed to model it with the pressure gradient effect fairly effectively, but that doesn't mean we're right. And I'll show more work tomorrow indicating that we may not be. But if you have this particular field of sea surface temperature gradients in the North Pacific, which is from the Reynolds OISST product, which is okay but noisy, you get some pretty substantial gradients. Now these are SSTs, but anywhere you get a gradient, which is all over the place, it doesn't have to be hot to have a gradient, you can get these effects. So if the wind blows over it, and we naively assume that we can calculate Ekman upwelling, that all this evolves, enough time passes that these systems come in equilibrium and upwelling actually happens, you get this kind of upwelling. If you work without that response, you get this kind of upwelling. And there's a huge difference. Now, I am not going to tell you that this is correct, but I am going to say that there's a lot of extra ocean mixing that happens because the ocean or the atmosphere responds to the ocean in some way. So here we can actually look at the percentage differences, and in many cases it's an over a 30% change. It's an order 1 impact. So what's cool about this is we can take that method for calculating a curl, which is doing the Ekman upwelling, and I can use it as a spatial filter. I can calculate for here something on a 500 kilometer diameter and something at a 600 kilometer diameter, and I can subtract the 500 one from the 600 one, and that automatically gives me the variability on scales between 500 and 600 kilometers. without going through all the Fourier stuff that's not going to work well for this kind of application. And you can see that it's bigger spatial scale than these smaller ones. You can also see that the cyclonic activity is on a bigger spatial scale than the anticyclonic, which is typical because that's what should happen in nature. And you can see that it gets bigger divergences as we get to these smaller scales. Now, at some point, this response is going to break down. It's not going to happen. Things are not going to be persistent enough. But we're still talking 100 to 200 kilometer scales here, 200 to 300. For SST gradients, these are substantial, and they should have a fairly persistent wind perturbation, even if not persistent winds over them. So you are going to get some fairly big changes on these scales. But the question then as we go down to the low end of meso and submeso is how persistent are these effects? I can argue that at 20 kilometers they're probably there without too much trouble. But as we go smaller and smaller down, in fact at 25 we know they're there, people observe them. So these are outstanding questions. We don't have a satellite wind yet at the scale we want, and that's the big push we've been trying to make with NASA to do that. And actually the next group that'll put one up maybe before NASA, the only other group working on it is the Indian Space Research Organization. If we can get one of these up, it'll be much better for coastal and mesoscale or sub-mesoscale work. Thank you.
Thanks very much.
Mark, the meteorological forcing we use in our operational system is the NCEP NAM forecast, which is about 12 kilometre resolution. You know, there are better model-based products, but which is comparable to something like ASCAT, I guess, 12 kilometre resolution. But the thing for us is the time sampling. You know, we've got diurnal winds. That's really important for coastal dynamics. So is there any effort to create a constellation that would be able to, or an analysis system that would be able to bring in the higher frequencies?
Yes, Tony's writing that proposal this month. No, seriously, he actually is. So then the other thing you think about, though, is you're saying 12.5, but you mean grid spacing, right? Yeah. And over the ocean, I didn't say this, but the resolution is actually about 6 times the grid spacing. At that scale, you're losing about half the energy that should be there. And then it just gets worse and worse as you go down. So that's part of the reason we need to get to much finer scales. We want kilometer scale products to get up to a reasonable resolution or finer. So the diurnal cycle, we've been talking about that over lunch today, trying to get that into the products. We think we have a way of doing better. There are for NCEP, working in regions you work in, there are actually products out that do hourly winds. I don't think they've ever been validated, so I wouldn't necessarily use them, but I consider testing them first.
You meaning satellite products, or?
No, it's, well, they don't tell us. It's a model product and something, and then that's a simulative model product.
Okay, high resolution rapid refresh, yeah.
Yeah, so yeah, we don't use them for anything yet.
So yesterday I showed the number of buoys or buoys around the United States that make measurements of over-ocean winds. Mm-hmm. What are your thoughts on expanding the network or the need for more observations of those winds, in situ observations?
Well, I think I'll make the same point John did, is that for the, I think you did as well, that for the surface, we don't need as much if we can get in close to the coast. So I think putting up a satellite with higher resolution is a better answer if you're willing to deal with the sampling. Now, our experience is if we put up one, India will put up one, and China will put up one. We might not get the data from China, or I might have to get it from Europe, but it can be done. So we'll get a constellation that you need to do that kind of activity. If you have other reasons to have the buoy there, then that makes more sense. And of course, that's not hard to do. But the other thing is, for all the physics of the coupling, we want a wind relative to the surface current. And that's actually what the satellites measure. And the buoy doesn't measure that. And that becomes a problem when we're trying to use the buoy winds for physics, because we don't measure a surface current. The current right at the surface is very different than the current 15 meters down. Very different. And even HF radar is analogous to a current about 1.5, 2 meters down. We've been doing some tests on that recently. So we really want to measure the wind and the current, because the other issue is we do need the currents, because if your currents in the model are in a different place than the currents in the real world, we need to either data assimilate them into the right place or have a physics that can correct for that, and otherwise you get a very biased forcing and you get the wrong eddy kinetic energy in the fields. It's not good. Sorry, long answer.
So it's a very nice overview talk, and I was talking about this time sampling issues in coastal areas. I mean, there's weather radars with Doppler, which are measuring, clouds and winds up pretty high. Is anybody using it for coastal application for driving ocean models?
People use it for wind power, which is about 180 to 120 meters, and they're still going down, extrapolating down to get that. I've seen one person use it for oceanography, and he's still having trouble. But we were looking actually then at what he's seeing and what I'm seeing in the satellite data where we do the curls, and they line up. So I think there's a potential for taking it further, but it only works so far away from the coast because the Earth is curved, and the further you go away, the higher the point corresponds to. So you're limited to about 150 kilometers if you want to play that effort, and it's tricky.
Thank you. So it's a follow-up question to John's questions about diurnal cycle in mid-latitude. So I always thought that in the tropics, the phasing of diurnal cycle is important, right? Because it's a coupled system. And for most of the mid-latitude ocean, higher latitude ocean, the diurnal cycle, to me, is just part of the high-frequency variability that matter for generating, say, inertial circulation, and therefore mixing. But I guess there's an exception where you have land sea breezes. That's when the phases of the diurnal cycle become important, right? So how well do NWP product resolve the diurnal sea breezes? Is it difficult? Because, I mean, if you get the land temperature, right, and then you ST constraint, isn't that nailed down already? I wonder. If so, not, it's got to be taken care of in this synthesis wind product.
It's not well handled. So the timing of the diurnal cycle depends a lot on the overlaying motion of the wind, and it's competing or working with that, and it changes the phasing of the land sea breezes. The other place where it gets interesting is gap flow, like through Tehuantepec Pass. And then the other issue that comes up in many places, the semi-diurnal cycle is actually stronger than the diurnal cycle, and that has to be captured. So one of the advantages of having rapid scat up was that we went through sampling the diurnal cycle. It was a very slow process through the cycle, and we could use that with several caveats to look at these features. And it was disturbing how large these signals were, and we're not capturing those in current wind products, satellite or model. And that's one of the things we want to try to improve in the next generation of products. So if we're going to do that, then we have to go to these higher resolution and time products, because otherwise it's not usefully putting it in. So there's more motivation to go to that. How well or how accurate they'll be, I don't know, but it'll be better than what's out there now.
Could I ask a second question? Yeah. Actually, if you mess up the phasing of the land sea breeze, but you get the magnitude right, let's say in the NWP model, how bad is it for an ocean model, fine ocean model?
We're looking at you, John.
Yeah. Is it that terrible if I get the magnitude right of land sea breeze, but the phase off? 3 hours, not opposite phase. Few hours. It's terrible because
3 hours out of phase is a 90-degree phase error. Yes. That's changing upwelling, SST. If you have a coupled model that should be feeding back to force the land sea breeze, then it's going to struggle.
Yeah. So Tony, the answer then comes to is are you sensitive to the application? So the upwelling, the
That's
transport
right.
on
Yeah,
and
yeah.
offshore.
Right.
This is a Navy guy, and they're going to be somewhat sensitive to that.
Thank you for all three.
Thank you.